Good morning. Today we will see this impact of modes of climate variability. We'll talk about monsoons and some patterns of teleconnections, and some of them don't have yet studies about projections, because some of them are not well reproduced by the models. So there are some that are still being studied and analyzed to see if it's possible to say something about the impact in projections. Okay. So what is a mode of variability? There are some patterns of anomalies that can be anomalies of pressure, of wind, of geopotential, anomalies in general. And there are some places that show this kind of anomalies in preferred ways. And they occur very frequently in the atmosphere or in the ocean, depends on the region we are analyzing this kind of modes. And many of these patterns have opposite anomalies in one place compared to other places. So they are related to many things. They can be related to sea surface temperature, with convection in some places, with the upper level circulation. So we will talk about this kind of patterns and the relations. But how to identify one mode of variability? One very simple way is doing correlation. If we do a correlation of one point, for example, let's take this point here, and we do a correlation. This is the equation of the correlation. We have one point and the other points, and here is the anomaly, where you get the variable and you remove the climatological mean. And then you correlate this point with all the other points. And then we can see which places, in which places we have positive correlations and in which places we have negative correlations. So if you, for example, this is a map of correlations with that point there in sea surface pressure, sea level pressure. And we see that all this region here have positive correlations, and all this region here negative correlations. So this is the mode that we called southern oscillation, and it's related to a convection over the Indonesia region, and high pressure or low pressure in this part of the Pacific Ocean. And this pattern is also related to El Niño. This is why we called ENSO El Niño Southern Oscillation, because both patterns have a relation. What does this mean? We have a normal circulation like this. This is a normal circulation that occurs between the Indonesia region and the Pacific region. That is, this region is as I told yesterday, is a very active region because there are lots of islands here, and the ocean can provide the humidity to the atmosphere, and then there are lots of convection and precipitation in this region. And then the air is going up here, and the westerlies are strong, and there is subsidence. The air is going down in the East Pacific, and then in the surface there is the trade winds going to west. So this circulation is called Walker circulation. It's a zonal circulation near the equator. So when there is this El Nino years that many of you already know, this convection is displaced to Central or Eastern Pacific. And all this circulation here is interrupted, and the subsidence is not here anymore in the West Pacific, but is over Amazon region and Northeast region. So the displacement of this circulation is one very well seen characteristic of the El Nino influence over South America, and in other regions as well, because all the circulation is changed. And in La Niña, which is the opposite condition of El Nino, but it's similar to the normal condition because there is a stronger ascent here and more convection here and less convection here. So this circulation is more intense in La Niña years. And what happened with the sea surface temperature? Why is this circulation is connected to the anomalies in the Pacific Ocean? Because here, in the normal condition or La Niña, these winds, the trade winds, they remove water from the surface, and the water from the depth of the ocean can rise. So the water in the ocean, in other depths of the ocean, are colder than in the surface. So that water comes to the surface, and there are negative anomalies here. Because this wind is very strong. But in the El Nino, what happens is that this trade wind is weakens. It weakens, and then there is no cold water coming to the surface, or there is less colder water coming to the surface. So we have warm anomalies in this part here, and in many regions here, or central or eastern. So all these warm anomalies that usually happens in the west part of the ocean are going to all regions of the equatorial Pacific. And this is one pattern this is a schematic only, but this is a real pattern in 1 month of 1983 when we had a very strong El Nino. And we see here the anomaly of sea surface temperature. So let's come back here. There is another way to identify the teleconnections or the modes of variability. Is through UF analysis, the empirical orthogonal function. It's a method that where we have anomalies in a domain that we want to study during a period. Can be any period we want. If you want to show interannual variability, we need to show long time, long period. And then we have these anomalies, and we apply this method, this a very common method that has been applied in many studies. And then we get the percentage of variance related to the total variance for each mode. And then this variance will give the dominant patterns. What are the dominant patterns? The patterns that have the largest percentage of variance. For example, if we have 3 patterns with 50%, and the rest, there is the other 50%. So the first can be 30%, the second 20%, and the third 10%. So we should choose these 3 first as the dominant patterns. But the dominant one is the first one that has the largest variance. And then we have also, with this method, we have the time series of the amplitude for each mode. Because we have places where we have positive anomalies and negative anomalies. But there are different phases. So if the amplitude is positive, that pattern will stay like the mode that we see. I'll show you an example. It will be easier to see, okay? So coming back to the El Niño, this is a very old picture, 1986. But it shows the global influence of El Niño and La Niña. So only to show that this is not a local feature. It's a feature that occurs in the Pacific, but it affects all the world. And many other places here in other studies have been shown to be affected also by El Niño. And in recent years, it has been shown that there is not only one kind of El Niño, because anomalies can happen in the eastern part of the ocean, and the anomalies can happen in the central part of the Pacific Ocean. And also, there was some features that that occur together with these anomalies in the equatorial ocean. So we call this, that is the normal one, canonical El Niño, or canonical La Niña when it's colder waters here, when the anomalies occur in the eastern part of the ocean. Here's one example only. And here when the anomalies are in central part of the ocean, but besides this, there is these other 2 negative anomalies And it was called Modoki El Nino because of this pattern here. Positive in this region, that is this region A here, and negative in these two regions. And here is the canonical, only to show where the anomalies are. And in this paper, we called Modoki plus A, because besides the index that Modoki had calculated, the anomalies in this part here, in this area, should be greater than 0.7 of the standard deviation. So we need to be sure that here we have positive anomalies. Okay, and why I'm saying this? To say that both El Niños, these two kind of El Niños, have different impacts in some places. For example, in South America, the canonical, here is September, October, November, and December, January, February. Canonical has this kind of pattern, opposite precipitation anomalies in north and south. But in Modoki plus A, we have different anomalies. You see, here we don't have positive anomalies in the south. And here the anomalies are in the southeast and northwest. So it's necessary to know what kind of El Niño is occurring to know how the impact will be in some places. Okay? And this Modoki has impact also in Australia and maybe in other places that they are being studied. So here is only to show how the models behave in relation to this kind of anomalies, SST anomalies. These are models of CMIP5, and this is another kind of method that is used to show these modes of variability. That is a method that related to variables. In this case is SST in the Pacific Ocean, in this region, and precipitation in North America. So the method related this to variability, and here we have positive anomalies in this region and negative anomalies here, because the domain was only the Pacific Ocean. So here there is one pattern that looks like the Pacific decadal oscillation when we have positive anomalies here and negative anomalies here in the positive phase and the opposite in the negative phase. And then here is observed data. And here is the model. Each line here is one model. Okay. So we see that the general pattern looks very similar. And the lines here are the zero anomaly line. And here is the correlation of precipitation in North America and this pattern that we see that is very good, 0.7. Okay, this is in this paper, Polade all that is in the reference also. Oops. So here is one observed time series of... question?
Hi. Are you saying that the model uses an empirical relationship between what's happening in one place and the other? It's not a physical transfer of energy? You're saying it uses this covariance method to determine teleconnections?
Yeah, this method used to relate two variables. So you do an UF, combine the UF in two set of data, and they need to be correlated.
And that is in the CMIP model? That correlation is in the model, or that's analysis after the fact?
This one here is observed.
Yes.
Is observed, and this is using model results. Yeah. Okay. Well, we see that the SST is quite well reproduced, but the precipitation is not so good, because here we have this kind of opposition of sign, and in the models, we can't have this opposition here. There's only this, in the west part, it's okay, but in the east part, the models can't get the influence. Yeah. So here is observed a time series of intensity of El Nino in region 3, which is near the east side of the Pacific Ocean, and El Nino in region 4, that is in the west part of the ocean. So to separate these two kind of El Ninos. And the red is El Nino in region 3, and the pink is El Nino 4 in west part. And also La Niña. La Niña is when the temperature are negatives, and this El Nino positives. And here the intensity is measured by the value of the anomaly. Then there is this line here, which is showing the trend. And the trend is a little bit negative for El Nino 3. That means the intensity of El Nino in this region 3 is decreasing with the time. And this is observed, it's not projections. And the other region, there is no difference, there is no trend. It seems it's happening at the same, with the same intensity all the time. But there are some papers that show that Modoc El Nino is increasing with time. Okay, I'm not showing here because so many information, and but is one thing that is happening. Now,
regarding that shift towards increased Central Pacific, and what can be a driver? Because it seems multiplicator shift. What do you think would be the driver of this more frequent Central Pacific or Modoc? What is changing now in the background?
yeah. Well, there are some theories about the interaction between the atmosphere and the ocean. So, if we have different circulation in the atmosphere, then the anomalies in the surface will will behave different as well. So if we have a convergence of winds in different parts of the ocean, the convection would occur more to the east or to the west, and depends on the intensity of the trade winds. So there are still some studies about what is, but it's mainly this kind of interaction. So we need to know if in a warming world, what will happen with the El Nino. And there are some studies about these model projections. And if we think if you think that the anomalies or the SSTs in the Pacific Ocean are increasing, we should expect that there will be more El Niños. First thing we can say about this. But the El Nino is calculated. The anomalies of El Nino are calculated in a certain period of time. So if we do the anomaly, if you calculate the anomalies in a period where the temperature of the sea is already larger than today, the anomalies will be the same or almost the same, because we are getting the climatology differently. If we compare the climatology of the future period compared with the climatology of the present period, certainly we'll have an increase of temperature. But if we have the same period and we get the anomalies for this period and the anomalies of other periods, we can't say that one is larger than other one. And this has been analyzed in many studies. And the conclusion, I'll show you here, the projections of the standard deviation of pressure that's related with the Southern Oscillation Index, that is related to the pressure at one point in the eastern part of the ocean with the pressure in the west part of the ocean. So the standard deviation of this index is plotted here. This is from CMIP3, and this positive here is positive changes in standard deviation. So it means an increased variability, and here a decreased variability. So here there are some models that show that there will be an increase of variability of this index that's related to ENSO, and the other models say that there is a decrease. So what is the conclusion? And this red here, are the models, because here you see there are many models, are the models that represent the El Nino better than others. So if we had all these models here in this phase here, let's say, we could say, oh, okay, the models that represent better the El Nino are showing an increase of variability. But there are 3 in this set that show an increase, and the other 2 that are good as well show a decrease. So one difference of one model is not enough to say anything about this. And here is the standard deviation in Nino 3. This is SST. This is pressure, analysis of pressure, and this is analysis of SST in CMIP 5. And we see here many set of data of results. Here is the pre-industrial. Here the 20th century. Here is with projection of 4.5, and here 8.5. So here, there's 3. We don't have too much difference between the pre-industrial to the XCP 4.5, and a little bit of increase in the last projection. Okay, but you see, it's not so high, this difference here. But this scheme is showing the El Nino conditions that we already talked about, and the changes in the Pacific SST, not in El Nino here, but only thinking about what would happen in the Pacific SST with the global warming. So here we see that the temperature will increase, and the temperature will increase in not only here, but in all regions of the Pacific. And this will give a condition of weak trade winds, weak easterlies. And weak, because this gradient of sea surface temperature and pressure, this drives the winds. So if we have less gradient west-east, then the trade winds will weaken. And if the trade winds weaken, what happens? There is less cold water coming to the surface. So in this region, we'll have less cold water, or less anomalies, if we're thinking anomalies now. And if we do, this is calculated, this figure is calculated removing the mean of this area here. So we have temperature in each grid point, and we have the area mean of temperature in all this area. And this blue is not saying that there are cold waters there. It's only saying that it's colder than the area, because everything is warm. But what this figure says is the warming is greater in the equatorial region, and is less in this region here. And this is in the AR5, because by that time there are not many papers showing that the El Nino will increase the frequency or intensity. We well, someone told me that there is one recent paper saying that the frequency will increase and the intensity will increase as well. When we see the figures of precipitation anomalies, we see that there is a pattern that looks like an El Nino intensified, because there are more precipitation in the east part of the Pacific, and other features that we see in South America, for example, with more precipitation in the south and less precipitation in the north. And these patterns are very much related to El Nino conditions. But there are still studies being conducted to show what would happen in the future. Here is another figure that I showed yesterday in March, April, May, and this is September, October, November. And we see that there will be, in the projections, an increase of temperature. For example, here, the shading is the previous, here, 1980 to 2005 period, the sea surface temperature. And this is the future. The future is in the contour. So this contour here is 30, but the previous one is 28. If you see this shading here is 28. So all the oceans are really increasing temperature. Now let's talk about the modes of variability now in the Northern Hemisphere. And I will talk about North Atlantic Oscillation, Pacific North America pattern, Northern Annular Mode. And there are two multi-decadal oscillations, that is PDO, or the Atlantic multi-decadal oscillation. But we will not talk about these two modes of variability, okay? We will talk about these three only. So this is the pattern of North Atlantic Oscillation. What is this pattern? In the North Atlantic, we have one law that is in the Iceland law. And we have the Azores high. We have these two climatological features in the circulation, atmospheric circulation. And when the Iceland law is stronger than normal, and the Azores high is more intense than normal, so this is showing a pattern that is called positive phase of the NAO. It's an oscillation. Why? Because if this law is weaker than normal, the anomaly will be positive. And if the high, Azores high, is weaker than normal, would be negative anomaly. So this sign change from one phase to the other phase. And here is the time series of the amplitude of this North Atlantic Oscillation. And why this is important? This figure shows an influence of the North Atlantic Oscillation in United States and Europe as well. So there is the positive phase. The positive phase, there is a very strong law there, and the westerlies are very strong in this phase. And all the storm tracks, we'll talk a little bit about storm tracks, but storm tracks are paths where the storms are displaced, moves. So these storms have some preferred regions to be displaced, to move. So they are called storm tracks. And then as this wind is very strong at high levels and also in low levels, all these storms are displaced to north. So the region of Mediterranean and southern Europe, all these regions are dry in this period of positive phase. And the north of Europe have more precipitation because of this, the passage of these storms. And another thing is that if there is this strong westerlies in north latitudes, this this makes the cold air that can come from the polar region, they can't reach the North America or Europe because of this. These strong winds act as a barrier to this cold air. So the temperature in North America and in Europe will be warmer than normal in the positive phase. But another thing is the Azores high will be stronger, and then the trade winds are stronger as well. And this can have an impact in IPCC. In the other phase, that is, we have the law is weaker than normal, so we have higher anomalies, and then the westerlies are weak, and then the storm tracks can be moving southwards of the normal. And then the north part will be dry, and the south part of Europe will be wet. And the same happens in North America. And then with weak westerlies, the cold air can go to North America and can go to Europe. So they have cold periods in this phase. And the trade winds will be weaker in the Azores region. So what are the other teleconnections in the Northern Hemisphere? This is one paper, very famous paper in 1981. That was the first time when it was shown in the same figure, all these kind of teleconnections. And we see that, well, we'll talk more about this one here, that's called PNA. It's Pacific North America, because it affects from the Pacific to the North America. And there are other patterns like oscillations, like this one, and in the same year there was this paper by Horrell and Wallace that was relating this pattern with the heating of sea surface temperature in the equatorial region. And now we know that there is this pattern of wave train. What is a wave train? We can see this with the alternating centers of anomalies. And we call this Rossby wave trains. Okay? And the same happened in the Southern Hemisphere. And we will see that it's called Pacific South America. Then there is Pacific North America and Pacific South America. Okay. And these kind of oscillations we can see here. This is East Atlantic pattern. East Atlantic pattern, we have one signal here and a position here. It's not the same as the North Atlantic because it's a little bit displaced to south. And we see that there is a seasonality of this mode. Generally, in the winter time, they are stronger than in the other seasons. And here is the North Atlantic oscillation. You see the difference from this one. This is, the opposition is in the higher latitudes. And the West Pacific, see here, there's an opposition of anomalies in the north and in the middle latitudes. And here, the East Pacific, and this is the PNA. And this PNA affects very much the North America, because if we think in a positive phase, it will be, if you think about the pressure, high pressure, low pressure, high pressure, low pressure. Or if we think in the high levels, would be a ridge, a trough, a ridge, a trough. And this pattern is strengthened during the El Nino, because this circulation, this anomaly circulation in the equatorial region or close to the equatorial region is very much related to convection and then the disturbance of the high level circulation that can then propagate these wave trains to the extratropics. So it's an interaction between tropics and extratropics, this kind of PNA and PSA. And here, if we have a ridge here, we have some conditions in the atmosphere, and here with the trough here, we'll have cold air coming to this southeast of North America. And here we'll have warm because the air will go from the low latitudes, and then it's a kind of ridge and trough. Okay. And what are these influences? So I don't know if it's too, it's good to see, but here's in the positive phase. So is this that I told you, this is would be high pressure or high anomalies, geopotential anomalies, and here is low anomalies or a trough. And And this will affect very much the temperature, as I told you. Here will be warm and cold. And in the other phase, there will be negative and positive here. And the temperature will be the opposite. So we have always think in these modes of variability as two phases, positive and negative. And the impact are many times the opposite. This is a simulation because we need to know if the models can reproduce this pattern. And this is a simulation by the Brazilian Earth system model. In reality, this model is still coupled ocean model, but it's being developed to be an Earth system model. And in this figure here, we show the NSEP and ICAR EUF2 that represents this kind of pattern. And here is the model simulation that is reproducing quite well these two centers here, but is not getting nor this and this other center here. So the annular modes. What are the annular modes? We saw that Pacific North America and Pacific South America, we have the same kind of triggering that is from the equatorial or tropical region. But we have also similar modes in the North Polar region and the Southern Polar region that are called annular modes. And then we see that there is one opposition of phase between the polar region and the mid-latitudes. When there is anomalies, negative anomalies in the southern polar region, there are positive anomalies in the middle latitudes. And the same occur in the North Hemisphere. We have negative anomalies and positive anomalies in the middle latitude and negative in the polar in the positive phase. Why the positive phase is related to negative anomalies, we can ask. Because these negative anomalies are related to the vortex over the South Polar and over the North Polar region. There is a cyclonic vortex in these two regions. So if this cyclonic vortex is stronger than normal, then we'll have negative anomalies. If the vortex is weaker than normal, then we'll have positive anomalies. And this oscillates. Sometimes we have positive, sometimes we have negative, because of the intensity of this vortex. And this kind of pattern is seen in all the vertical layers of the atmosphere. And it's a barotropic structure that is we can see in the sea surface pressure, we can see in the middle latitudes, we can see at in the middle level of the atmosphere, in the high altitude. So we see also that this is related to the circulation. in here is plotted the zonal wind anomalies in the southern hemisphere. That means these winds are stronger than normal, and these winds are weaker. And you see that the same structure happens here. Why is that? Think about cyclonic circulation that is like this in the southern hemisphere. So this circulation will give westerly strong winds here. And in this middle latitude, we'll have anticyclonic circulation that is like this. So both circulations are increasing the intensity of the zonal winds in this part here. And in the other phase, in the negative phase, we'll have anticyclonic here, in the polar region, and cyclonic here, which gives a weakening of the westerlies in the higher latitudes, but a strength of the winds in the subtropical latitudes. So this shows also the intensity of the polar jet or the subtropical jet. And the same occurs in the North Hemisphere. This to show that the models of CMIP5 could represent well this north annular mode, that is in CMIP3 and CMIP5. And in the southern hemisphere, the belt is more annular in some periods, in some seasons. But anyway, it's called annular mode in both hemispheres. In the southern hemisphere, let's see the main modes of variability in the southern hemisphere. I will show only these two southern annular modes that we just showed in the other figure. But here we can see more this kind of negative and positive, and in the other phase is the opposite here. And the Pacific South America is similar to the Pacific North America, but we see in these centers of negative, positive, and this pattern is affecting very much South America.
This pattern is more similar to PSA 1 or 2?
Here is if we don't do the zonal anomaly, this pattern is represented by the UF2. And probably the 3 will show the PSA 2. But if you want to say two patterns of PSA, because there are a displacement of these two patterns, but we need to do a zonal anomaly, and then the first mode will show the PS1, and the second mode will show the PS2. But it's an evolution of the centers. Yeah. Yeah, this is only to show what we talk about how can these wave trains be formed. So if we have SST anomalies in one place close to the equator, we have the the humidity going up and then doing convection, and then there is divergence in high level, convergence in low level, divergence in high level, and then anticyclonic circulation in both hemispheres. And this change, because this will change the circulation at high levels, and this will be starting this kind of wave train, of Rossby wave train. What is a Rossby wave? When we have the wind in one latitude, for example, the Coriolis force tends to push that wind north or south, depending on the hemisphere. So if we change that latitude, the Coriolis force will change, and then to do the vorticity constant, because the absolute vorticity is the vorticity, relative vorticity plus the vorticity from the rotation. And then for this, we need to have an opposite sign of this relative vorticity. So the wind can do another circulation, south or north, but then this will propagate, because every time it's going north or south, this equation, this absolute vorticity needs to be constant. So you increase or decrease the relative vorticity anomaly. Only to remember, because many of you already know this from the school. So this pattern has an influence, as I told, in this South Atlantic convergence zone. That's a band of cloudiness over South America. And this is the correlation of convection in in this region of South Atlantic convergence zone and the meridional wind. And you can see this pattern of PSCA that is related to convection in the Indonesia region here. So here is a simulation by the Brazilian Earth system model of this pattern of PSCA. Here is the reanalysis, and this is the model. It can get the main features. And in the Hadjane, we can see also that this model can represent both modes of variability. The south annular mode, that is this one, here with one phase, one anomaly in the high latitudes, and the opposite anomaly in middle latitudes. And this is the PSCA pattern. And this is for only one season, and EOF 1 and 2, without filtering and without doing the zonal anomaly. But the models, in general, can reproduce all these models, PNEA, PSCA, and the two annular modes. Now, what happened with the changes? Here is a simulation with hydrogen 2, and here is the projection with the RCP 8.5. We see that there are some changes in the position of these centers. And also there is this study which shows the difference of pattern of PSCA in this period here and the other period in the future. And also there are some differences in intensity, mainly intensity and in position. But there are few studies that show what happens with these patterns. So it's necessary more studies to have confidence that the patterns are changing or the intensities are changing. But what we know is that the patterns will continue in the future. The patterns will not change to other kind of patterns. This is one thing that we can say, but we can't say for sure that it will be increased or not. I think that there will be some changes, because if the convection will change in the equatorial region with this warming, maybe this pattern will be more intense, but this is only some schematic thinking. And changes in the South Atlantic convergence zone. We have done this kind of study with historical, that is the present time, or the period of CMIP 5 historical, with this model here. And this is with the RCP 8.5, and we see that the pattern is the same, that is related to the variability of the South Atlantic convergence zone. We have this kind of dipole here over South America. When the South Atlantic convergence zone is more intense, we have more precipitation here and less precipitation in the south. And when we have more precipitation in the south, there is less precipitation in the South Atlantic convergence zone. So this is a very well-known pattern, and but we see that in the projections we have the same pattern. The only thing is that this intensity is projected to be reduced, and this will be increased. The intensity is increased. And this is consistent with the projections of precipitation that show an increase of precipitation in the south. And there is also some results similar in this paper here. Now, about the southern annular mode that we talk a little bit, that are opposite anomalies. And here I am showing 1 month of January, which is summer in the Southern Hemisphere, and July. And we see that there are differences. In the summer, the annular pattern is more defined. But in July, we have also some centers, very strong centers around the hemisphere. But, well, we already said this. In the positive phase, we have strong polar jet and weak subtropical jet. And in this phase, we have the opposite. So these opposite phases will imply in intensification or disintensification of the jets. And this is important for the places that are in the south part of the continents. Australia, South America, South Africa. So here is only to show the influence of this mode. And here is a set of extreme precipitation in this part here. And here the dry conditions in this region. And this is a composite of extremes, wet cases and dry cases. And the geopotential anomaly shows the opposite conditions for the phase of this south annular mode. And this is also connected to PSCA, because all these two modes, they combine together to strengthen these wave trains over South America. So what happened in the projections in the future? Deixa eu ver a hora que estou... Some people are going out. This is what I was looking the time to see if it's, but there are some 20 minutes. Okay, yeah, okay. So what happened is this is the sea level pressure difference between the future period and this period of CMIP 5, that is 86 to 2005. So we see that there is an increase of negative anomalies in the polar region and an increase of positive anomalies in the middle latitudes. That means there is an increase of the positive phase of sun. And what is related to this? We saw that in the positive phase, the polar jet was stronger and the subtropical jet was weaker. And this polar jet will be related to the movement of the storm tracks as well. So there will be a displacement southwards of the storm tracks. And here is the changes in storm tracks in both hemispheres. In the North Hemisphere with XCP 4.5 and XCP 8.5. And the negative is when there is a decrease of density of storms. And we see that all this region here is projected to have a decrease in storms and an increase in the north in this region here, which is West Asia and the Pacific Ocean. And here there is an increase in the low latitudes that maybe is related to the tropical cyclones. But in the southern hemisphere, we see stronger here this displacement. A reduction of storms in this region and an increase in the higher latitudes. Yeah, and this steepling here means that at least 90% of the models agree on the sign of the change. It's different information related to that hatches in the precipitation and temperature that I showed yesterday. Okay. And this is another figure that shows the displacement of the jet in the vertical structure, and the negative is colored with blue, and the positive is where the winds are being increased. So there is an increase of the zonal mean wind polewards and in all seasons, you see. And this occurs also in the North Hemisphere. In both hemispheres, we can see this change in the jets. Now, the projected changes. How the models are projecting changes in this North Atlantic Oscillation, North Annular Mode, and Southern Annular Mode. So here we have 4 seasons, and the first one is North Atlantic Oscillation. And this red and green are observations. And this black line is the ensemble mean, and this gray are the dispersion of the models. So we see that for this North Atlantic Oscillation, mainly in the I think that only September, October, November shows a positive trend. But the other seasons don't show. Why? Because you see the dispersion is very large among the models. So when you do the average of all models, there is no change, positive or negative. So we don't have still confidence to say that the North Atlantic Oscillation will increase the positive phase or the negative phase. What about the North Annular Mode? So we see that in some seasons we can see an increase, a slight increase. In this season, nothing in June, July, August, and a little bit here. But you see, the dispersion is very high as well. If the dispersion would be only in one sign, we could say that, well, the sign of all models are showing that the phase will be positive, or the positive phase will increase with time. So the only mode that we can see that there are some changes that we can say, well, it is increasing in the projections, is the Southern Annular Mode. You see, there is this positive phase, trend of positive phase in all seasons, Although there are also some dispersion, but the majority of models are showing the same signal. Okay. And this is another way to see this projected changes for the North Atlantic, the North Annular Mode and Southern Annular Mode. And this is the zero line, and this is the seasons as well. And we see that the majority of models show an increase of the north annular mode and the southern annular mode. In all the more for the southern annular mode, and this is related to sea level pressure. Related to PNEA and PSCA. PSCA, I showed some results with the projections, but this is the observed trends. And there is a PNEA index that is the time series of the second mode of variability. Then we have this index that is observed to be increased along the time. Well, you see that there are lots of variability, but the trend shows a positive trend in this PNEA. And related to PSCA, there are many ways to calculate an index for PSCA. So there is the PSCA, which comes from the UF amplitude of time series. There is Caroli index and U1 index, and these two indexes are calculated doing an average of 3 points in that centers of anomalies in the Pacific Ocean. So there is observed decrease of this index of this from the positive phase to the negative phase. Okay. So we'll stop here, and we'll talk about monsoons after the break. Do you have any question for this part? Okay. There?
Thank you for the presentation. I have two questions. Possibly one, I'll draw you back to what you took us through yesterday about model uncertainty. I think the commonly discussed is the actual model certainty, but there's this aspect of scenario uncertainty. I don't know how it's measured. Could you be having information about it? Then secondly, is through what you have taken us through now about the dominant modes of variability, especially the EOF. I'm not sure of how this is decided upon, deciding how many modes of variability do you want to calculate. Because, for instance, if you decide on having 3 modes of variability, the dominant mode, all the modes will explain different percentages of variance, unlike someone who has calculated 5 modes of variability. So, which is more or less like the standard? What's the standard number of variability are you supposed to calculate when you are doing EOF? Thank you.
Well, the significance first of the results are calculated by showing standard deviation of several models, seeing if the phase is there is an agreement in the phase of many models. Sometimes errors in the variables that can show that model, that mode in each model. So, for example, if we have a North Atlantic oscillation, And we know that the model has a systematic error in pressure and in the north location or in the southern location of this mode. So we need to take that in account, related to the intensity. But if all the models show the pattern, of anomalies, and we can say that the models are reproducing the pattern. But when we look the time series of the amplitude of these modes, maybe we don't have the same amplitude compared to the observation, because the models they have the own variability, and only when there is a very strong forcing for that patterns. For example, when there is a strong anomaly in the Pacific Ocean or Atlantic Ocean that's connected with that pattern, then the variability would be similar. Otherwise, sometimes the model can show one variability and the observation can show another variability. This is common in a long run integrations. Related to the second question, what is? Sorry, I don't remember.
Regarding calculation of EOF, for instance, is there a standard number of modes of variability you are supposed to calculate? I was giving an example. If you calculate 3 EOFs, they will explain different variances, unlike 6. Well, normally we get the mode of variability that is, as I told you, the variance should be high. So the first one is one that you should look as a dominant mode, because it will represent the largest variability. Then you go to the second one. The second one, if the variance is close to the first, or if it's larger as well, you can consider that mode. But then from the 3 or 4 and 5, and then they can show more details of the variability. And problem is they are not showing a dominant mode. Yeah. Okay. Anybody else? Okay, we can return, and if you remember another question, we can talk. Thank you.